this is our presentation on steam drying techniques, and additionally forced convection in a circular tube, which will model in ANSYS. My name is Yuri Murnovich.
My name is Emily Hembry.
My name is Alex Savage.
For this project, we decided to look into superheated steam drying techniques. So what it does is it's a way to remove moisture from a system. Superheated steam, compared to traditional standards, works in an oxygen-deficient environment, which allows for higher safety standards because nothing have combustion, safer processing. It's overall more improved efficiency compared to traditional convective air heating techniques. The way it works is you take your material and you have it in this chamber, and the feed inlet is coming in with superheated steam. And it has a higher specific enthalpy, which allows you to absorb more of that heat. So it's going to allow a greater heat transfer to occur. So it'll dry your objects quicker. It's most commonly used in food processing, such as pulp and paper, and the textile industries.
These are some of the traditional drying techniques. We have three, them being hot air drying, spray drying, and vacuum drying. Some of the benefits for hot air drying include it's the most common type, it's low cost, and it's a simple design. Some of the drawbacks are it's got low efficiency, uneven drying, which can lead to a longer drying time. For spray drying, the benefits are it's very fast, which can lead to a high overall production rate, as well as consistent product quality. Some of the drawbacks are it's very energy intensive because of how fast it is, and the equipment to carry out this kind of drying is expensive. For vacuum drying, the benefits are it's conducive to sensitive materials, and it can also produce better quality. The drawbacks are it's high cost, slower throughput, and it's a complex system. The applications of hot air drying can be used in the grain and agriculture sector, as well as lumber and wood, paper and pulp, and just general bulk material drying. For spray drying, it's used for milk powder and whey, powdered beverages, detergents and cleaning chemicals, as well as pharmaceuticals. Vacuum drying can also be used for pharmaceuticals, but more specifically heat-sensitive drugs, biological materials, specialty chemicals, and electronic materials and components.
So comparing traditional and advanced techniques for steam drying, we can see that some of the advantages for the traditional techniques include simple operation and easy implementation, as well as lower initial capital costs and a broader scope of flexibility for application. This is a very simple process, as it only needs a heat generation source and a way to move the air across, basically just a heater and a fan to dry the goods. But some of the disadvantages to that are it does require a higher energy consumption. It also has a lower thermal efficiency as well as longer drying times. You also get a variation in the product quality due to the hot air being blown onto the product, as well as it has a large environmental footprint. So when looking at advanced techniques, some of the advantages are it has higher efficiencies and faster drying times, as well as improved product control and reduced oxidization. It also has potential for closed loop systems for the improvement of product quality, but some of the disadvantages are that it does have a higher initial capital cost, as well as a more complex design and system control, and it's not suitable for all materials and processes.
So building off of what Alex mentioned earlier, you may be wondering, why is it more efficient? Well, we can look at the specific enthalpy. If we were to look at the specific enthalpy of superheated steam versus saturated steam, you would notice that superheated steam has a higher specific enthalpy. Now, what does this mean? It means that when you're trying to dry your pulp or paper, that superheated steam is going to allow for more absorption from it. Superheated steam is going to perform better at drying.
So for superheated and low pressure superheated steam drying, we have two methods. One of them is convection. You can either let the steam pass through the material or let the material be suspended on a cloud of steam to dry it, as well as a roller method, which passes the material over rollers that are heated by the steam itself. It's useful for web-like materials, such as paper, nonwovens, and veneer, and it has a uniform drying of large volumes, as well as a low risk of damaging the product, as well as keeping the product pure without any degradation.
For the second part of this project, we were looking at forced convection in a circular tube. We are going to use ANSYS to model this. We will create a simple copper pipe to model in fluid, and we will set some parameters and create a meshing to run the simulation. Simple assumptions that need to be made is the no-slip wall condition, uniform inlet temperature, and velocity.
These are some of the parameters that we use for our ANSYS fluid. simulation. For the pipe geometry, the outer diameter is 20 millimeters, the inner diameter is 10, wall thickness is 2.5, and then the overall length of the pipe is 1 meter. Our inlet conditions, the flow velocity is 0.5 meter per second, the inlet temperature is 300 Kelvin, and then for our turbulency modeling, we have intermittency, intensity, viscosity ratio, and intermittency ratio all equal to 1, with a turbulent intensity of 5% and a turbulent viscosity ratio of 10%. Additionally, we have a constant heat flux parameter applied to the surface, and it's 5,000 watts per meter squared Kelvin. And this is the 3D model of the simulation.
So just setting up some of the basic parameters in ANSYS, our working fluid is going to be water. So we can go ahead and use from the ANSYS database the density of water and some of the thermal properties such as the conductivity and the viscosity. Material choice was copper, so we're going to also pull from the ANSYS database. So for our ANSYS simulation, setting up some of the viscous model settings, we're going to keep mostly everything default, but we're going to select transition SST for equation, keep our alpha set to 1, and we'll let everything else remain.
2 hours later.
Here is a meshing of our pipe in ANSYS, which you can see the inflation lines going around the working fluid, which will help us resolve our boundary conditions.
These are some of our mesh statistics. Just a disclaimer, due to the nature of the student license for ANSYS, the mesh can only top out at 1 million. Our number of elements is close to 1 million. It's actually 870,080. These are our mesh metrics. The skewness, the average skewness is 0.17522, with the ideal being around 0.1. And then for our orthogonal quality, the average is 0.83013, with the ideal being 0.8. So that's pretty good. This is a graph for our temperature results of our simulation. You can see that it starts off really cold and then it gets a little bit warmer towards the edge. You can also see the wall temperature. It starts out cold at the very beginning and then heats up as it goes through and then cools back down towards the end. Even temperature throughout, it's on the colder side. This is a cross section that shows that it's extremely hot on the surface of the pipe. These are the numbers. The range is 3 to the 2 to 3.06 to the 2, so not that much variance. These are our velocity results. From the cross section, you can see it's faster in the middle of the pipe, and then it gets slower towards the boundary layer of the pipe. However, the velocity profile is uniform throughout the entirety of the pipe.
So for the XY plots for the temperature, we can see that there's a pretty good temperature distribution. You see the highest temperature at the two edges of the pipe. The flat portions are the actual pipe itself, and then you see a sharp decrease in temperature reaching towards the middle of the pipe flow. For the XY plots for the velocity, you can see that expected behavior of the boundary layer being slow at the walls and then faster in the middle of the pipe.
Some of the equations we use, we just pulled from this class and other textbooks. We use simple equations like having to figure out the friction factor, the Reynolds number, Prandtl numbers, the Newsett. We also important to note is the Golinsky number and the Ditsus-Bolzer number, which we needed in this simulation.
This is a table with some of our hard-coded values here. The X values are determined in diameters as opposed to total length of the pipe. If you remember the diameter, the outer diameter is 10 millimeters. So 40 diameters is 400 millimeters. We've got our wall temperature, our bulk temperature, our bulk velocity, pressure, friction, Reynolds, Prandtl, and our heat coefficient. After that, we have our Newsell number, our Dittus-Bolzer and Nolinsky approximations, and then these are the percent differences.
And as you can see here, we've plotted the Newsell number that we obtained from the fluid flow from ANSYS, as well as the Dittus-Bolzer and Nolinsky approximations from the fluid parameters found in ANSYS. You can see that the Newsell number that we calculated is a bit lower than the Dittus-Bolzer and Nolinsky approaches, but you can see a convergence towards our calculated Newsell number becoming in line with the Dittus-Bolzer approach, which is to be expected as the flow develops downstream of the pipe. Potentially a longer pipe flow would have allowed a better convergence on these, but due to the limitation of the meshing and capabilities of ANSYS Fluent Student, this Newsell number that we obtained is reasonable and within a allowable percent difference.